Hello everyone. So today we are gonna study advanced technique of DSU, which is disjoint union set. So before that, the prerequisite is you must be aware of DSU, disjoint set union. But I will give you a brief. So basically, what a DSU is, for example, we are making a graph. There are few nodes. Initially, they all are disconnected. Now, for example, uh, then we get one edge between these two nodes. Now if we are asked how many disjoint sets are there, so we will see this is one set completely because the both node are connected, so they individually are not one disjoint set, but they both are. This one is another one, this one is another, so in total there are five. If I connect them, now there are only four. If I connect this, now there are three. If I connect this, now there are only two disjoint set. If I connect this, now there is only single disjoint set. And so how do we calculate this? Again, I'm saying this video is not for the ones who don't know about disjoint set union. So because I will be covering it in very brief, the main video will be about the weighted DSU. So in brief, if I show you the code, so how DSU work is, we take a parent array and rank. Size is not required, actually one of rank or size is required. So if we do rank by union, so we take n, so we resize, resize the parent and rank array n plus 1 because I'm taking one base indexing. So there are two functions. One is find ultimate parents. So what find ultimate parents does is it returns the ultimate parent of you. Or for example, like if there are these four nodes, now if I have to find ultimate parent of 3, parent of 3 is 2, then parent of 1 is 1, then parent of 1 is 1 itself, there's no more parents, so that means the ultimate parent of 3 is 1. So this is what ultimate parent is, and this is how we calculate this. And then we have a union by rank function. So imagine now initially there are two, these three disjoints, and now we get one edge between. Now we get an edge between 6 and 3. So to join these two disjoint union set, we use the union function. So it basically checks if they are already in the same union, that it doesn't do anything, and it will merge the lower rank one into the higher rank one, because in this way we can limit, uh, I mean, so the tree doesn't get too long. So if we attach the lower one to the higher one, we put a foundation to the tree height, it won't go more than log n. So yeah, this is basic DSU. But now how about weighted DSU? And again, I'm mentioning, if you don't know DSU, then you can follow some other YouTube video for that, and after that come here for weighted DSU. Now to explain weighted DSU, let me take an example. For example, there's a problem where we are given n, so we will be given number from 1 to n, and now we are given queries. So the queries are of type, like we will be given a x, y and d. So basically what this query tells us is that x minus y equals to d. So there can be many query. For example, if I so this means is x1 minus x2 is 5, and x2 minus x3 is 6. Now see how using these two we can also calculate x1 and x3. Now imagine there's one more, 4 and 5, 1. So x4 minus x5 is 1. Now can we calculate x1 minus x4? You will notice we cannot, because there's no one that's connecting them. But if we have some common terms which occurs both with 1 and 4, for example, if I do this 2, 4 and some 5, so now I have x2 minus x4 is equal to 5. So now if you want x2 and x5, we can get this using this. And if not, even if this was x2 and x3, still we can use this one, this one, and this one to get x5 minus x2. So basically how is this works is, if I represent it as a node, so imagine this is x1, x1 is connected to x2, now x2 is connected to x3, x4 is connected to x5. Okay, we still can't get that. X4 is connected to x5, and x2 is connected to x3. We already had that. Okay, now if you want x5 minus x1 or x5 minus x2, clearly we can't get that because there's no connection. But if we make any one connection, we will somehow be able to always manipulate the equation such that we can get that. For example, if we are given x5 minus x3, now we can get x5 minus x2 as well, x5 minus x1 as well. You can try this it yourself. If the all nodes are somehow connected, the difference between any two nodes can be written. Okay, so the question is, we will be given queries like this. Okay, so if the current query does not contradicts with any of the previous queries, so basically the previous occurring map, for example, if we are previously given x1 minus x2 is equal to 5, x2 minus x3 is equal to 6, from this we get x1 minus x3 is equal to 11. If we add both the equation, we get 11 and x2. But now if we get another query which says x1 minus x3 is equal to 10, so this one is contradicting that one. So in case of such queries, we don't take that as, and rather return a false. We ignore that query and print something to tell, I mean, yeah, you can return false to tell that the query is not valid, and if it's valid, then add the as and return true. So how can we do that? So okay, so if we think about this, initially all terms will be different, and as long as they are in different set, they can never be contradicting. The contradiction will only happen when we get a query of between two elements which are present in the same set. So it can contradict, and it might not if the value exactly matches with the what we previously had. So if we somehow can, okay, we are already making the, we can make the disjoint set already by using the disjoint set we discussed. But if we somehow also store the distance between x1 minus x2, x2 minus x4, and x3 minus x4 or x4 minus anyway, because if we know x3 minus x4, we also know x4 minus x3, so that doesn't matter. If somehow we can store all the relation we are getting with time, we can do our job. So can you think of a way in such that in the disjoint set we are using, we can also store the now if you think what is this 5, 1 to 5 indicates, this indicates there's a edge between 1 and 2 and the weight of edge is 5, right? What does 236 indicates? There's an edge between 2 and 3 and the as weight is 6. Usually what do we have? We only have the queries up to here. We don't have this 561. We only have the first two terms, which indicates there's an edge between these nodes. So now if somehow we can store this weight as well, our job will be done. So it will be good if you pause for a minute and try to think how can we do that. Okay, I hope you try. So now let's discuss. So now let's try to build this. Okay, so these are the edges we have. These are the queries 1 to 5, 2, 3, 6, 3, 5, 1. So let's take the first edge. Now imagine we have a disjoint set. Okay, so we have nodes up to 5, 1. Okay, so initially we get is node 1 minus node 2 is 5. So we take an edge of weight 5, connect it to this. Now we get node 2 minus node 3 is 6. So either we can do it like this, but you see the problem in this is the height of tree will keep increasing, right? And if at any point you need, for example, 1 minus 5, you will have to just each time traverse the whole tree. So how about we use the concept of rank? Just like since we are using DSU, we are supposed to use rank, right? So initially, for example, these are the all the nodes. Okay, so now we get 1 and 2. Now initially the rank of both is same, which is 1 or 0, whatever we choose to initialize with. So in case the rank is same, we can merge anyone into anyone. So it's better we merge 1 into 2, and the weight will be, if we are merging, if we are merging the first one with the second one, then we will take positive weight, and if we want to do it like this, then we indicate negative weight. So basically if there's an s going from here to here, so we will, this means x2 minus x5 is equal to 1. This means x1 plus 5 is equal to x2. Okay, so this is the denotation I'm using, just to not have any confusion. So this means x1 plus 5 is equal to x2, which also means x1 minus x2 is equal to, okay, wait, that's not what I meant. Okay, I was wrong. So I mean, how am I denoting is this, if there's a edge pointing outwards from a node, that means that node minus the weight is equal to the node that to its pointing. Okay, so now the first one is done. Now we want to merge 2 3 and the weight is 6. Now we see the rank of 2 is 1, the rank of 3 is 0, So we should merge 3 to the lower rank to the higher rank. So we taken as from 3 and merge into 2. Now see, if the edge would have been from 2 to 3, it would have been plus 6. Now since it's from 3 to 2, it should be minus 6. Now we have another edge, 3 to 5 is 1. Now again, and we don't take the rank of node, we rather take the node rank of ultimate parent. So the ultimate parent of 3 is 2, and the rank of 2 is 0, I mean 1, and rank of 5 is 0. So again we should merge 5 into 2. Now in this case, how are we going to merge this? Because we have the difference of x3 minus x5 is equal to 1. Now how we do in disjoint set is we usually try to merge it with the ultimate parent itself. So we want to merge it with here only. So but now what should be the weight? Because it would have been minus 1 if we directly merged it with 3, but now we are merging with 2. So how we can calculate the is this, that is like, when we are going to find the ultimate parent, in each node we will store the distance from ultimate parents. For example, this node is 5 from ultimate parent, this node is minus 6 from ultimate parent. And now, so now if we see, this was minus 1 from this, and this is already minus 6 from ultimate parent. So this should be minus 6 plus minus 1 minus 7 1 from ultimate parent. We can also try this. See, x2 minus x3 is equal to 6, x3 minus x5 is equal to 1. So now we get, if I add both the equation, I get x2 minus x5 is equal to 7, which x2 minus x5 is equal to 7, which indeed is equal to ours. Ours is minus 7 because our edge is from 5 to 2. If there would have been an edge, if we go this way, then this will be plus 7, right? This is minus 7 because we are going this way. So now how are we going to implement this? Now let's first see how we can check using this. So now if each time a new query comes, for example a, b, and the difference is d, we can find the ultimate parents of a, ultimate parent of d, and using that we will get like the difference between okay. So now what does this each as gives you? This gives us the difference between x n minus में x ultimate parent, right? For example x5 minus x2 is minus 7, which is indeed. So by finding the ultimate parent, the weight of, if their ultimate parent are same, now we see what's their distance from their ultimate parents. Say that if the distance, now we have, say d1 is the distance of a from ultimate parents, d2 is the distance of d from ultimate parent. So now what is the distance between a and b? So basically d1 is xa minus xp, d2 is xp minus xp, we need xa minus xb, so we can subtract them. So xa minus xb would be d1 minus d2. Now we can compare this with this d, and now if this is equal then it's fine. If this is not equal, then it's a invalid query, or a query which is inconsistent with the previous data given, so we disregard this query. Okay, so now how are we going to implement this in code? Let's see. Okay, so this is a normal disjoint set. So what we want to change is, we not only want to store the parent, but we also want to store the as between the node and its parent, right? So we will take a pair. So the first number of the pair will be the node, which is the parent, and the second one will be the weight of the node by which it's attached to the parent, right? So initially, what should be the weight of? Initially, it itself is the parent. Every node itself is the parent of itself, so the weight will be 0, right? So we make a pair. Okay, rank of every node will be 0 only. Size we are not using here, so I'm commenting it out to avoid confusion. Okay, so this is all the change we needed in the initializer. Now, while finding the ultimate parents, we won't be returning just the parent. We will also be returning the weight from that parent, right? Because we needed that. We use that to compare if the two nodes were same. Like we got d1 and d2 only, then we can compare, right? So we want to return both the parent and the distance from it. So we will return a pair. So now, okay, so we will see if parent, this will be the base case. What should be the base case? If parent of u dot first is equal to u itself, then we can just return, right? Right, if the node itself is its parent, then we can return that. That's the ultimate parent, because either we can return u comma 0, but the parent will have itself that only, so that's fine. This is the base case. And what should we do in a general case? Imagine the parent is not equal to, so obviously we will find the parent of parent, so we will do that using, okay, now this will help us find the parent of parent. And now let's store this parent of parent in a temp. We will discuss this why. So now we have, so what will temp have? The temp will have the parent of this node, which is current parent, and it will have the weight between the ultimate parent and this node. So now if we want weight between our child node and the ultimate parent, we will just add the current weight it into the, so now what will be the weight of current node with the ultimate parent? This will be temp dot second and plus u dot second, right? Because if you see, say this is one node, this is one node, and there are some nodes in between, and this is the ultimate parent. So the distance between this is x, this is y. So what will be the distance from of this node from this node? It will be x plus y, right? So here inside the temp dot second x is there, and inside our parent u dot second y is there. That's why we are adding that, right? So Now let's assign this to temp dot second only, so we can return this only. So now our temp has the weight from current node and ultimate parent was already there, so we can return temp. Now we should also do path compression, so we don't have to traverse log n each time. So we can do that by simply just updating the parent of current node, right? So like if 1 2 3 the weight are 2 2, now we will find firstly this and then this will return the ultimate parent is 1 and the weight is 4, so we can just erase this edge and directly attach it there, so next time it will be faster with an edge of 4. So this is what we are doing. Okay, so this was all we need to do for the file ultimate parent. Now while the union, how will we do that? Firstly, in this case it will be a pair, not int like in regular DSU. It will be pair this time. So yeah, now we have ultimate parent of u and ultimate parent of v. Now we check if the ultimate parent are same. We don't need to do anything, right? Now if they are different, now if they are different, then we should merge the parent with lower node in to the parent with higher rank. I mean the parent with lower rank should be merged with the parent with higher rank. So if the rank of ultimate parent of u is higher, so we should like attach then all the nodes of v also to u. So how do we do that? For example, there's this one graph and this another graph. Now we want to merge this one to this, so how do we do that? We just take the ultimate parent and merge it to this ultimate parent. Now they both are part of same set, right? So this is how we do that. Also here in union we will also have one more thing, which is the weight, because there's a whenever there will be edge we will also be given a weight x, right? Okay, so now we want to change the ultimate parent of second. It should be the parent of current one, but it will be pair, right? We also need the distance. What's the distance between them? So how do you think we can get the distance? Say we have these graphs. Now imagine we get a edge here. Now we want to merge this to this. How do we get the distance? So when we get the ultimate parent, we will get what we will get. Like we initially discuss, it gives us xa minus xp, right? So this will give us xa minus x3 minus x1, and this will give us x4 minus x6, and this is 6. So now we want x1 minus x4, and we are given an edge between x3 and x6. So how do we get this? What we want is x1 minus x4. So can you see how can we manipulate this to get that? If we subtract this one, this will cancel this, and yeah, we will add this and subtract this, which will give us x1 minus x4, right? So mathematically, what should be the equation? If you see, the first pair will have the ultimate parent, which is 1, and it will have x3 minus x1, and there's an edge between 3 to 6, which is of some weight k, and we will, here in the ultimate parent, we will have the ultimate parent and x4 minus x6. So what will be the weight of this edge? To calculate the weight of this edge, what we should do is, and this indicates x3 minus x is equal to k. Say it's some, let's say x3 minus x1 is d1, x4 minus x1 is d2, and this is k. Now we want this as, no, we want this as, right? So this would be x4 minus x1. So how do we get x4 minus x1? Okay, this will be x6 minus x4 rather. We have x6 minus x4, we have x3 minus x1, we have x3 minus x6. So how do we obtain x4 minus x1? To do that, we add this and subtract this. So this will basically, we have two pair. So p of u dot first, this will be the weight of this as p of u dot first plus k, and this one we want to subtract. Wait, what did we wanted? We wanted x4 minus x1, and this is x6 minus x4. So yeah, and we subtract pv dot second. Yeah, this will also be second. So this will be the weight of the S. So now let's write this first. Let's calculate the weight. It was p of u dot second plus x minus p of v dot second. Right. This is the weight if we are merging v to u, which is indeed what we are doing here. So yeah, this is how it's done. Now what's the other case is if the rank of u is less than rank of v, then we need to merge u into v, right? Not the other way around. So in that case, what we should do is, it should be first Okay, it should be first because second one is weight, and this should be first too. Yeah, and this should be second. It's fine. And this should be first travel. So now we should assign the use parent as v. Also now what will be the weight this time? We when we were making an s from v to u, it was weight. Now if we are making an s from u to v, what will it be? It will be minus weight, obviously, right? See, if an s from here to here is weight, so what will be an s from here to here? It will be minus weight. So we don't need to calculate that again, we can just do minus weight, and this will be p of v dot first. And in case the rank are equal, in that case also we can do this only. We can just in case of equal, we just need to make sure we do one thing, is we increase the rank of whatever one we are merging into. So here we are merging into u, so we should increase the rank of u. Yeah, that's our work. Okay, this seems about correct. What is wrong here? Did we miss anything? Okay, this is else, so we can't have condition, right? So yeah, it's fine now. So yeah, this is the final uh, changes we need to make to our DSU structure to use it for a weighted case. I don't think there are too many changes, like we just change this type, and while assigning parent we do this anyway. The only extra thing we did was this line. In union, the extra thing we did was calculating this weight and passing this here. Mostly it remains the same. So yeah, so now that's the final code we have. I will share the code if you need. And now to I will also share a link of problem in the description, which you can solve, which is based on weighted DSU only. I will also upload solution of that problem in some days. Meanwhile, you can try that and let me know if you could solve this. Thank you.